Hello everyone, this is Chinnaiah Kalpana here. In this video, we are going to solve a differential equation using variation of parameters method part 3. So let's get going. Problem: solve y double dash plus y dash equals to 1 by 1 plus e power x or d square plus d of y equal to 1 by 1 plus e power x using variation of parameters method. Given differential equation, y double dash plus y dash equals to 1 by 1 plus e power x, considered as equation number 1. We can write y double dash as d square y by dx square and y dash as dy by dx equal to 1 by e power x. Now write d square y by dx square as capital D square y, where d is the differential operator. Let's write dy by dx as capital Dy equal to 1 by 1 plus e power x. Now take y common from these two terms, we'll get d square plus d into y equal to 1 by 1 plus e power x, which is in operator form. Equation 1 in operator form is equation 2, right? It is in operator form. So f of d into y equal to some function of x where f of d is d square plus d and r of x is 1 by e power x. Okay, now we'll find the solution to our problem, equation 1 or 2, using y equal to yc plus yp. Okay, we'll find the general solution using y equal to yc plus yp. We'll get yc using the auxiliary equation, and later using yc we'll find yp and with some formula. Now coming to the auxiliary equation, the auxiliary equation is f of m equal to 0, where f of m equal to, we have f of d square plus d, right? Let's replace the differential operator with m, so that we'll get f of m equal to m square plus m. Now the auxiliary equation becomes m square plus m equals to 0. Take m common from these two terms, we'll get m times m plus 1 equal to 0. Now equate each factor to 0. Here m plus 0 is, m equal to 0 is one root, and from m plus 1 equals to 0 we'll get m equal to minus 1, another root, right? M equal to 0, minus 1 are the roots of our auxiliary equation. Therefore the roots are real and distinct. We know that when two roots say m1 and m2 are real and distinct, then yc looks like c1 e power 1 root into x plus c2 e power another root into x. Now coming to a complementary function, yc equals to c1 e power 1 root 0 into x plus c2 e power another root into x, which gives us c1 e power 0 plus c2 e power minus x. Since e power 0 equals to 1, so we'll get c1 into 1 plus c2 e power minus x, which gives us c1 plus c2 e power minus x. Therefore yc equals to c1 plus c2 e power minus x. Okay, we got yc. Let's now find yp. Let yp equal to, now replace the constants or parameters with some functions of x, a and b. We'll get yp equal to a plus b e power minus x, where a and b are functions of x. And compare yc with c1u. plus C2V or YP with AU plus BV to find U and V, where U is 1, V is e power minus x. See? U is 1, V is e power minus x. Here A and B are given by, A is given by integral minus V into R of x by uv1 minus v1 into dx, and B is given by integral u into R of x by uv1 minus v1 into dx. So if you notice, we are having uv1 and minus v1 in both the formulas. So we'll begin with uv1 minus v1 and later we'll find a, b, yp and finally the general solution using y equal to yc plus yp. Here v1 is nothing but derivative of v with respect to x. u1 is nothing but derivative of u with respect to x. U is 1 into derivative of e power minus x minus v into derivative of u. This gives us 1 into derivative e power minus x with respect to x is minus e power minus x minus e power minus x into derivative of 1 with respect to x is 0, which is equals to minus e power minus x minus 0 equals to minus e power minus x. Therefore, uv1 minus v1 equal to minus e power minus x. Now coming to A. A is given by integral minus v into R of x by uv1 minus v1 into dx, right, is equals to minus integral v. See, here we are having R of x a fraction, so we'll write the integrand as minus v or v by uv1 minus v1 into R of x, okay, for our convenience, into dx. This gives us minus integral v is e power minus x by uv1 minus v1 is minus e power minus x. So let's not take the minus outside the integral, okay. R of x is 1 by 1 plus e power x into dx. Here minus e power minus x gets cancelled and we'll get integral 1 by e power x dx. We can write e power x as reciprocal of e power minus x. Okay, we can write this as 1 by e power minus x plus 1 by e power minus x into dx, which gives us e power minus x by e power minus x plus 1 into dx. Let e power minus x plus 1 equals to some t. Now differentiate on both sides with respect to x. Which gives us derivative of e power minus x with respect to x is minus e power minus x plus derivative of a constant is 0 equal to dt by dx. From this we'll get minus e power minus x equals to dt by dx. From this we'll get minus e power minus x dx equals to dt, or e power minus x dx equals to minus dt, right? Let's replace e power minus x dx with minus dt and e power minus x plus 1 with t. Now coming to this integral, we can write this as integral e power minus x dx by e power minus x plus 1. This gives us integral, replace e power minus x dx with minus dt and e power minus x plus 1 with t. Or we can write it as minus integral 1 by t dt, which gives us log mod t or minus log t. Since t equals to e power minus x plus 1, so just replace t, we'll get minus log of e power minus x plus 1. Therefore, equal to minus log of e power minus x plus 1. Now coming to B. B is given by integral u into R of x by uv1 minus v1 into dx. Here r of x is a fraction, so we'll write the integrand as u by uv1 minus v1 into r of x into dx is equals to u1 by uv1 minus v1 is minus e power minus x into r of x is 1 by 1 plus e power x dx, or we can write it as minus integral 1 by e power minus x into 1 by 1 plus e power x into dx. We can write reciprocal of e power minus x as e power x. We'll get e power x into 1 by 1 plus e power x dx, or we can write this as minus e power x by 1 plus e power x dx, right? Let 1 plus e power x be some q. Now differentiate on both sides with respect to x. Okay. Derivative of 1 with respect to x is 0 plus derivative of e power x with respect to x is e power x equals to dq by dx, or we'll get e power x equals to dq by dx, which gives us e power x dx equals to dq. Now just replace e power x dx with dq and 1 plus e power x with q, right? We can write this integral as minus integral minus e power x dx by 1 plus e power x. Just replace e power x dx with dq. We'll get minus dq by 1 plus e power x can be replaced with q, or we can write this as minus integral 1 by q dq, which is minus log mod q or log q. Since q equal to 1 plus e power x, so we'll get minus log of 1 plus e power x. Therefore, b equal to minus log of 1 plus e power x. We got a and b. Let's now write or find yp. Yp is given by a plus b power minus x. Substitute a and b here. Minus log of e power minus x plus 1 plus b minus log of 1 plus e power x into e power minus x, which gives us minus log of e power minus x plus 1 plus into minus minus e power minus x log of 1 plus e power x, or we can take e power minus x common from these two terms. See, in the first term we don't have e power minus x, so what we'll do is we'll just multiply and divide e power minus x to the first term. Right? Now take e power minus x minus e power minus x common from these two terms. We'll get minus e power minus x of 1 by e power minus x into log of e power minus x plus 1 plus log of 1 plus e power x is equals to minus e power minus x of reciprocal of e power minus x is e power x. We'll get e power x log of e power minus x plus 1 plus log of 1 plus e power x, which is a required yp. Now coming to the general solution. Therefore, the general solution is given by y equal to yc plus yp. We have yc and yp, right? But yc is c1 plus c2 e power minus x, and yp is minus e power minus x of e power x log of e power minus x plus 1 plus log of 1 plus e power x. This completes the problem. So this is all for now. I hope you'll understand. We'll see you in the next video. Until then, bye bye.